How do you check to see if two different variables, both on their own and together, impact your data in a statistically significant way? Today, we're going to look at the Twoway ANOVA from start to finish, every piece of information and code that you need to be able to use a Twoway ANOVA on your own without a statistics package using the Python programming language. My name is Jacob. I'm a human factors consultant from Intrepid Protoworks. Alright, so let's get started. We're going to start off with some imports. If you do not know how to set up a Python programming environment, it's easy. We have a video on it at the very beginning of this series. Also in the same video, we show you how to get a data set like what we're using in this tutorial. All the code and the data we are using in this tutorial will also be in our GitHub for this series, which will be linked in the description below. If you've been following the series, these imports should look relatively familiar, and most of them are in a basic Python install other than scipy.integrate. So we do math, we need a couple of variables from it. We need scipy.integrate for our F probability distribution function. We're using decimal so our gamma function doesn't blow up. We're using CSV so we can read in our data. We're doing random so we can resample that data because working with 3 million data points isn't practical for what we're doing in this tutorial. And then we're introducing a new one, ordered dict, which will help us keep all of our information lined up. So we're going to start off with our gamma function. It'll take one input, which is z, and then we're going to immediately define a nested function, which will take two variables, t and z. Inside of that, we define e, which is math.e, which is approximately equal to 2.71828. And then we're just going to return decimal t time to the power of decimal z minus decimal 1 times decimal of e taken to the power of decimal of negative t. We are then going to integrate that using scipy.integrate.quad. If you're curious on how this works in more detail, you can reference some of our previous videos where we make use of this. We're using our own gamma function with decimal because it lets us put in some bigger values for degrees of freedom later on. We'll make ourselves a little bit more space and then start our next step. Now, our next function will be the F probability distribution function. It will take an F value and a degrees of freedom 1 and a degrees of freedom 2 for the numerator and denominator, or between and within, degrees of freedom between and within. We've done an entire video on just probability distribution function, so we're going to go ahead and speed through this next two functions where we define the probability distribution function, as well as a function to get the p-value by integrating the probability distribution function for f. Alternatively, we could also just use the cumulative density function for f as well. However, that is an entirely different video in its own right. Now, as you see me speeding through this, you'll notice that I spend a fair bit of time going through and double checking for typos. It's really important to make sure you spell decimal correctly every single time. It's a really mucked up looking function. There's probably a better way to write it, but this will meet our needs for today. Next, we'll just write a quick function for getting the mean. This is the same as we see in almost every single one of our videos. And that is all the prerequisite starting functions that we need. We're going to go ahead and actually make a placeholder for our Twoway ANOVA function, and then we're actually going to go in and look at how we prepare our data to go into this. So our Twoway ANOVA is going to take data, an alpha level, and we're going to have a Boolean variable that will tell us whether or not we want to get p from this. Now, we may not always want to do this, especially if we're just wanting to do a real quick analysis, because calculating p takes an inordinate amount of time. To calculate it to a decent degree of precision with a high number of degrees of freedom is a very time-consuming calculation using scipy. So now we're going to go ahead and start off using ordered dict. Ordered dict is a dictionary that maintains its order. It's ordered dict. A normal Python dictionary does not have this attribute. So we're going to start by defining a bunch of empty parts of this. So we'll do our first factor, we'll do gender by race. factors. That'll be an ordered dict. Within that, there'll be gender by race factors gender, which will be another ordered dict. Then within that, there'll be gender factors, or there'll be factors, gender, and then male and female. There'll be the same for race, race white, race black, and then we'll do one for each of our cell means, as well as one that will hold our entire data set for what we're looking at. Now that we have the structure of our ordered dict defined, we can go ahead and populate it with our data. This is going to be the same process that we've done in a number of other tutorials, with a few minor adjustments, and I'll point those out as we go. To control for a little bit of additional variability, we're going to also only look at people with a higher level of education, so 5+ years of college in this case. Now, let's go ahead and actually start adding a whole bunch of if statements. We forgot to add in the actual entire dictionary up top, the part that will hold all of our data. So let's go ahead and add that in real quick. So we'll do gender by race, then we'll just call it gender by race, and it'll be an empty list. Now, each data point is going to be added into multiple parts of this. So white male will get added into both the white list for race and the male list for gender. It will also get added into the gender by race total, the entire data set, and it will also get added into a cell, which will be the white male cell. All of these are necessary for how we're going to do the two-way ANOVA today. So we have a list in our dictionary that is the entire data set. We have a list that will be each level of each factor, and then we have a list for each individual cell. And it is because of this more complex data structure that I wanted to go ahead and go through this first before writing out the code of the two-way ANOVA. Note the way we are doing our cells is a little bit different. We're using AND statement. So if int row 2 equals 1 and int row 0 equals 1, it will go into our white male cell. And then comparatively, we'll go into each other cell. We'll have 4 cells in this model for our two-way ANOVA. If you're looking at how to do a two-way ANOVA yourself, and you're thinking to yourself, well, my design is not a 2x2, well, that's fine. Just add in the additional levels for each of your factors and have the appropriate number of cells. The way we're going to write the code tonight is going to be agnostic to the number of cells and the number of levels in each factor. Additionally, we're really close to the code that will be used for a three-way ANOVA and so on. The main difference with having more than 2 factors is how the interaction terms work. So if your sample was collected with a two-way ANOVA in mind, and you have the appropriate amount of data for your two-way ANOVA, in other words, each cell is the same size, then you don't necessarily need the following code. If you're following the tutorial for the educational purposes all in its own right, then you'll need to follow along with this part. But if you have your own data set and you're following along with your own data set, you don't need to resample the data. Populating the lists inside of the ordered dict is sufficient. So I'm going to go ahead and speed through all of this. This is pretty similar to what we did in our one-way ANOVA. We're just building, basically we're rebuilding what we just built above with a certain cell size in mind. You can also use this same method if you want to resample out of a data set where each cell is not the same size. That may not be the best way to go about it, but it is an option to go about it. We're building this in opposite order this time, starting with our cells. This is because we want to use the same data points across the entire board. So we're getting a sample of each cell that meets each condition, and then we're building our gender factor, we're building our race factor, and then we are building our entire data set, so our total factor or our total part. And one thing to note is that we are inadvertently reversing the order here. We'll adjust for that later on when we write out our Twoway ANOVA function itself. We follow the same pattern. We just swap out which cells we're taking from and which factors or lists we're appending to. And then we're just using a simple for loop to go through each cell and append it to the appropriate list within our ordered dictionary. Make sure to go through and double check you're appending to all the correct stuff. We'll make ourselves a little bit more space. And then we're just about ready to party. We'll go ahead and define our alpha. We'll define our get p as false for now, just because, as you will soon find out, it takes forever to calculate p with the code as we've written it. And then we'll go ahead and get our results and our degrees of freedom within from our Twoway ANOVA. That'll be the output. The results will be a ordered dict. And then it will take our sample, our alpha, and our p. So let's go ahead and go back up to the top and start working on our Twoway ANOVA. We'll start by deleting this pass line. Then we'll go ahead and define an empty ordered dict. We'll just call it model. And then we will create a empty variable, call it grand mean. We'll set to 0. We'll set I to 0. We'll use this to identify what part of our dictionary we are looking at, whether it's all of our data, our factors, or our cells. Now, if you are just using your own data set and you did not need to resample it like we did below, you do not need to use the part of the for loop that we're about ready to use. So we're going to do a for loop to loop through a dictionary. It works looping through an ordered dict, works the same way as looping through a regular dictionary. However, we just loop through it the same order every time. So the way we set up I is that the first thing we want to see is our entire data set. Then we want to see our factors, and then we want to see our cells. The way we assembled the resampled data below was in the opposite order. The cells are first, then the factors, and then the total. So we're going to do for key datum, singular of data, in reversed data.items. And then if I equals 0, so if we're looking at the entire set of data, we'll use this to get our grand mean as well as our sum of squares total. Get our grand mean, we just do grand mean equals get mean datum, and then our sum of squares, so that equals 0. And then we will loop through our data, and we will just add our squared deviations for our row minus our grand mean to the sum of squares. And then after that, we will add our sum of squares total to the total part of our model. Next, we will start working on each factor. So we'll do if I equals 1, and we will start by defining model factors as an empty ordered dict. Next, we'll go ahead and make a loop that will go through each of our levels in each of our factors. So we'll do for factor levels in datum.items. We'll get our factor mean using our get mean function we made earlier. Make ourselves a little bit more space. Okay, my notes, I skipped a couple lines, so let's go back. So model factors, and then the label, which will be factor, and we'll set that equal to an empty list. Next, we'll do SS factor, and we'll set that equal to 0. That stands for sum of squares for our factor. Now, we just need to make a loop to go through each level, get the name of that level, and to get the data in that level. So I'll do for level data in factor levels.items. And then we're back to where we're supposed to be with getting our mean for our level. So next we'll define sum of squares, and that'll be equal to the length of our data times our factor mean minus our grand mean squared. We will then add that to our sum of squares for our factor. With that calculated, we can then define our factor degrees of freedom. We'll set that equal to the length of our factor levels minus 1. Now we have our sum squares for our factor and our degrees of freedom for a factor. We can get our mean square by taking our sum squares factor and dividing it by our factor degrees of freedom. So now we have our sum of squares for our factor, our degrees of freedom for our factor, and our mean square for our factor. So what we can do now is go through and append that to the list that we made earlier. And we'll just go ahead and copy and paste and then do our sum squares, degrees of freedom, and mean square. So with that done, we can now go ahead and make ourselves a little bit more space and start in on calculating what we need to with our cells. So if I equals 2, we can then look at the cells for a data set. Start off by defining our sum of squares within equal to 0, our degrees of freedom within equal to 0, and then model cells equal to an empty ordered dict. Now we'll loop through our cells by doing for cell data in datum.items. Then we will get our cell mean, and we'll do cell mean equals get mean cell data. Next we'll do our cell sum of squares. We'll set that equal to 0, and we will do our degrees of freedom within plus equals the length of our cell data minus 1. Now we'll go ahead and make a quick for loop. We'll do for row in cell data, sum of squares plus equals row minus our cell mean, and we'll square that. Now for later use, we'll go ahead and do model cells cell, and we'll go ahead and put our cell mean into that. We will then go ahead and add our cell sum of squares to our sum of squares within. We'll go ahead and back out of the for loop, and then we can go ahead and make our mean squares within. This will be equal to our sum of squares within divided by our degrees of freedom within. And the last part to do for this big loop is to add 1 to I. Now that we've gotten all that, we have everything we need to start making our F ratios. But first we're going ahead and fix a quick typo. We have our cells nested 1 layer too far in. And with that, we can go ahead and back out of that loop and start with the F ratios for our factors. We'll go ahead and make a variable, call it significance, and we'll set to false. We'll go ahead and do for key row in model factors.items. We will then define our F as the third element of our 0 indexed row divided by our mean squares within. So the mean squares of our factor divided by our mean squares within. And then if we decide we want to calculate a p-value, we're making this an option because calculating p takes a long time. We'll go ahead and print out calculating p so we know that the function is working. And we'll define p as 1 minus get p from f, our f ratio, our degrees of freedom between our degrees of freedom within. Now if p is less than alpha, then we will set significance equal to true, and then we'll also go ahead and print out what our p-value is. That way, for all of us impatient people out there, we can see it right away. We're going to go ahead and round that off because we don't want a big number in a table. Otherwise, p will just equal not a number. That way we have something to put in our table that we make later. We gave ourselves a little bit more space, and now we can go ahead and add this into our model. So we'll do model factors, the key of that we're going through, and then we'll go ahead and end our F. And we're going to go ahead and round that to 4 figures because we don't really need much more than that for how we look at it when we're just reading it. And then we'll go ahead and also append our P, and then we're going to go ahead and append whether or not it's significance, or a significance variable that will say true or false. Before continuing, we'll go ahead and want to set significance back to false. And now we can go ahead and start on our term for our interaction. So we'll say sum squares all factors equals 0, and then we'll loop through and subtract out the sum of squares for each of our factors. Then we will want to go ahead and set our sum of squares all factors equal to itself, sum of squares all factors, minus the sum of squares within. Lastly, we will set the sum of squares all factors equal to itself plus sum of squares total. This is a little bit backwards from the way you might have seen it in a formula, but it's mathematically identical. Continuing on, we'll do degrees of freedom all factors, set it equal to 1, and then we'll do a quick loop that will be for key row in model factors dot items, and then we will multiply degrees of freedom all factors by our degrees of freedom for each factor. In this case, in our example today, it'll end up still being equal to 1. And because we're multiplying it, that's why we set it equal to 1 rather than 0. This lets us calculate our mean squares all factors, which will be equal to our sum squares all factors divided by our degrees of freedom all factors. Now I'm calling this all factors rather than an interaction just because when you look at like a three-way ANOVA, it won't just be 2 factors, it won't be a two-way interaction. We'll be looking at potential 3-way interaction and multiple 2-way interactions. So our f all factors is just going to be our sum of squares all factors divided by our mean squares within. Now we're going to do the same thing as we did before for calculating p. So if we want to calculate p, we'll start off by printing the calculating interaction p, and then we'll say p all factors is 1 minus get p from f degrees of freedom all factors and degrees of freedom within. And if p all factors is less than alpha, we'll set significance equal to true, and then we'll go ahead and print out the p-value for the interaction. Lastly, we will just go ahead and round off p for our interaction to 4 decimal places. And if we do not want to calculate p, we'll just do p all factors equals nan, not a number. Now our degrees of freedom total, we'll go ahead and calculate that and add that into our model. We'll start by setting equal to 0, and then we'll say for key, row, and model factors.items, df total plus equals our degrees of freedom for each factor. That gives us our degrees of freedom for each row. Then we'll add in our degrees of freedom within. And then lastly, we will add in our degrees of freedom for our interaction term. And then append that to our model degrees of freedom total. Now we just need to make ourselves a little bit more space. And with our space, we can go ahead and add in our information interaction term. So model interaction equals sum of squares all factors, the degrees of freedom all factors, the mean squares all factors, the f all factors, the p, and if it's significant. The last thing we need our Twoway ANOVA to give us will be information on our within, our error term. So we'll do model within error, and we'll say that is equal to the sum of squares within, the degrees of freedom within, and the mean square within. Now we can go ahead and return our model, and for convenience, we'll just have it return the degrees of freedom within right here as well. Delete the leftover space, and we are ready to start processing the output. So let's go ahead and scroll down to the bottom and start typing out how we want our output to appear once the Twoway ANOVA is ran. So we're going to use string formatting to this, and this is denoted by the curly braces. Now you can put a colon and then have it be justified, and then how much space you want to be justified. So that'll give us something that prints out looking like a table. And we can do dot format, and we can put in either variables or strings that we want. We go ahead and change these to match how much space we think each variable will need. We'll leave the first part open just because that's just going to be the labels. We'll do sum of squares, degrees of freedom, mean square, our f, and our p. Then we will go ahead and just print out our header. Now we can go ahead and start the convoluted process of formatting and outputting the data that we get from our model or our results. So we'll say for key, data, and results.items. If the key equals factors, we'll go ahead and set our table string equal to this. So we'll use the same format each time. We don't need to add the end of character line. And we'll use the dot format again as well. And rather than an empty space, we'll say our key. And then we'll do our row 0, row 1, row 2, row 3, row 4. And then we'll just go ahead and print out that table string. Next, we'll go ahead and say if our key equals our interaction, we can go ahead and print out the information on the interaction. And to do that, we'll just copy and paste most everything here. We'll just need to swap out row for data. Then if key equals within error, so we'll go ahead and print out the row for our error term. We can copy and paste that and just remove some of the parts of that because the error term only has the label, the sum squares, degrees of freedom within. And then we just need to print out our total. So we'll say if key equals total, and it'll be similar to the within error where we don't need as many terms. Also looking back at my notes, I see I made a little error. We need to have data 2 in there as well. I'll go ahead and round that to 4 decimal places. We'll also go ahead and round the sum squares, so row 0 for total as well. Now, if we decide to go ahead and get p, we can go ahead and put in a couple of statements that will give us some output that will tell us if the results were significant or not. So we'll say if get p for factor row and data.items, We'll go ahead and print off some statements, and we'll continue using string formatting, using dot format in a string like we've been doing. And we'll go and just speed through this. This is basically similar to what we did above, except we're just going off of if a factor is significant or not. We will also do the same thing for the interaction term. So this will give us a statement that you can use for your own standards or your own requirements. You can format to APA, or you can format it to whatever variety you need to, and you can have it just spit out, say, an APA formatted statement if you wanted to. The above isn't what I call like APA formatting. It's just what I put in for this example. So we'll go ahead and make ourselves a little bit more space, and then we'll do the last part of processing our output, which is to create a plot to look at the cell means. This is going to be very similar to what we've seen in previous tutorials. So we'll just import matplotlib.pyplot as PLT. We'll do plt.style.use BMH. BMH is my personal preference. You can print out these styles. You can see how we did that in previous tutorial. And then we'll go ahead and do positions as an empty list, labels as an empty list, and means as an empty list. And then we'll set an iterator I equal to 0. And then we'll say for key cell and results.cells.items, we'll say labels append key, means append cell 0, that will be the mean, and then positions equals I, or positions append I, and then we'll iterate I at the end of that. And that will give us the information to try to. This is a little bit different from what we did before. So it lets us be kind of agnostic to what we input into it. So we don't have to necessarily be repetitious. We can just put this in when we're using dictionaries. We carry the labels around with us already. So plt.bar positions means color equals gray, width equals 0.5, align center, error, color black, cap size 5. That last part might not be necessary. We'll leave it in anyways. We'll say the X label is sample incomes, the Y label is mean income in dollars, and then we will go ahead and label our graph. We'll say mean incomes for race and gender. We'll define our X ticks as our positions and our labels, and then we'll go ahead and just show our plot. And then we can go ahead and hit save and run it in a new dedicated terminal. And we forgot to put our brackets there, so fix that. And we forgot to put as a string, and we have another error. So we'll go ahead and troubleshoot that real quick. It looks like we said row rather than data. So we'll go ahead and fix that real quick and try running it again. See if any errors comes out. So we still have an error set. Int object is not subscriptable. I see we forgot to put this into a loop for our factors. We need to go through our factors. So we need to say for factor row in data.items and then put this into one more tab in. Now we can go ahead and hit save and run again. See if we end up with an error. All right, looks like we have everything printing out. No errors. We do need to work on our formatting a little bit, so let's work on that real quick. Oh, we also don't have our labels correct either, so we need to fix our labels. I'll get to that in a second. For now, I'm going to go ahead and fix our rounding. We don't necessarily need to see all the rounded or all the decimal places for our rounded information. So we'll go and round off our sum of squares and our mean square. That helps a little bit. Looks like everything's lined up now. Take a look at our graph. Looking at it, I also see that we're not getting our interaction term. So let's double check that we didn't misspell things. Going back up top, interactions. Okay, so we'll fix that. Look for any other places we may have made the same mistake. Yeah, so fix that there as well. Let's go ahead and play around with sample sizes. So let's up this to 200, run our Twoway ANOVA again, and take a look. We have an F ratio of 44 for our first factor, 34 for our second factor, 91 for our interaction. We'll go ahead and fix the formatting. So we're going to round off the decimal places for our sum squares and mean squares for our interaction term. We'll go ahead and save and run that again once we get that in there. Then take a quick look at our results, see if things are lining up. We've got a graph. Looks like things aren't quite lining up. We don't have our mean squares correct yet. So So I go ahead and round off the sum of squares within. We'll go ahead and also remove one of the unnecessary round offs up top. And then go ahead and run that again. Take a look if our formatting's better. Formatting is still off for interaction term. You can see that the graph looks good and we're getting reliable results as well. The F ratio is moving around some, but that's kind of expected when we're taking something as variable as income and sampling, only 200 people out of a data set of millions. So now that we have that working, we can go ahead and try getting P. This is going to take an inordinate amount of time. So expect your computer to just chug along for a while. Don't panic. It's going to take forever. We're going to go ahead and, through the magic of cinema, speed through this here. We'll see SciPy kick out a warning. What that warning means in our situation is that our results are so close to zero it's so close to zero that's within our margin of error. And it's going to give us a not number response as a result. But you can see our F values are pretty high. Our F ratios are pretty high. We double check our code, look through everything. And we're going to add an OR to make sure that we still get to print off. So it still tells us if it's significant. And we will see that it should report significant in this situation. We don't necessarily need to go back and run it again just for the sake of time, but it should go ahead and output the correct significance. I see I didn't go back and fix the issue with the labels printing. That just means that we needed to say factor and not key. And it should give us the correct name for each of our factors, being gender and race. Thank you for watching. If you have any questions or comments, please leave them down below, and don't forget to like and subscribe.